Hi everyone. So I'll wind up the discussion on instrumentation amplifiers by taking one design example. Since a lot of you, I think I saw a comment asking for, can you give us a design example? I mean, just showing a data sheet doesn't help. Can you just show us a design example as to how should a system designer go about choosing the right instrumentation amplifier? So I'll give an example from an ADC point of view. See, every system is different. The circuit is different that you're going to design. But I can talk about ADC. And see, if you are interested in applications of instrumentation amplifiers, you can look up the internet and you'll find lots of applications. But I'll just give an example. If you're, if you have seen all these vital monitoring, if you have gone through any health checkups, right? Or, if you have seen any of your relatives in hospitals, normally you would see there'll be a lot of probes connected from a human body, and you would see a lot of electronic screens displaying your vitals. In most of those devices, you will have some kind of an instrumentation amplifier being used. Okay, so the main reason is to reject common mode signals, where the probes can pick up some common mode signals and only amplify the differential inputs. That's what is the application of an instrumentation amplifier. So one example, okay, then how do I pick the right? I showed you guys a huge, a different plethora of differential amplifier specification. I mean, differential amplifier chips, and each chip had some chip had lower offset voltages, some chips had lower noise voltages, and lower noise voltages chips were priced higher. So I thought I'll give an example. How does the noise matter by doing a calculation for an ADC? Now let's say your instrumentation amplifier happens to be at the input of an ADC. So you are measuring some differential signal. It can be a sensor, heat sensor, or it can be you are measuring the electric potential on your human body, a vital monitoring system. You want to amplify that input differential signal. Okay, and then if you want to display some numbers, right? Let's say you're measuring your heart rate. These are all numbers that gets displayed on screen. So when those numbers get displayed on screen, somewhere in your mind you should think that there is an ADC which is digitizing that input, and all the processing happens digitally from there on. Okay, in some specific applications, medical especially, medical imaging and some interesting applications, the resolution of the ADCs can be very high. Okay, so when you talk about ADCs, the defining characteristic of an ADC is what we call as effective number of bits. I mean, I can have an ADC which is 20 bits, but if I measure its SNR, signal to noise ratio, it will not be corresponding to 20 bits. So what do I mean by that? Let's say you have an n-bit ADC. We can show that the signal to quantization noise ratio for an n-bit ADC is given by 6n plus 1.76 decibels. Okay, this you can show using assume a sinusoidal input, and then a full scale sinusoidal input, and from that you can derive that result. So I'm not going to the proof. You'll find this in most of the textbooks. I'll directly quote the result. So ADC engineers it will be like the back of their hand, so it will just be basic knowledge for them. So your SQNR is given by 6n plus 1.76 decibels. Now for a 20-bit ADC, this corresponds to a number of 120 plus 1.76. I'll approximate it to 122 decibels. So that is, if I feed a sinusoid to this ADC, let's say I feed a sinusoidal input to the ADC, and then plot the spectrum at the output of this 20-bit ADC, you should see a tone, and assume that for all the quantization noise won't look like a floor like this, but let's assume it's going to look like a noise floor. Then the signal power to the noise power, if I find the total noise power, assuming it to be a white noise, the signal power to noise power should be 122 decibels. But in many practical ADCs, it need not be that. Your SNR may just be, let's say your SNR happens to be your SNR is say 90 dB. okay, or 92 dB. Let's say your SNR comes to be 92 decibels. So you have designed a 20 bit ADC and you're expecting a SQNR or SNR from the measurement to be 122 decibels, but it turns out your SNR is just 92 decibels. We then define a term called effective number of bits. So we equate 6, we call 6N1 plus 1.76 decibels equal to 92 and compute N1. Okay, equate 92, 1.76, I'm going to call it 90, so 90 upon 6, I think 15 bits. So even though you have designed it for 20 bits, it's actually a 20 bit ADC, but the effective number of bits, its performance of an ADC is that of a 15 bit ADC. So we will say that the effective number of bits is only 15. So in these ADCs, what will happen is quantization noise actually will be very low, but it turns out there will be thermal noise or noise due to clock jitter. These are other sources of noise in an ADC. They will dominate the noise and they will be much higher. Okay, their noise due to noise, this is noise due to thermal noise, which can be due to the sampling circuits and anti-alias filters, okay, or comparator reference noise, okay, all that will manifest as a thermal noise floor. It turns out for this ADC, which is supposed to have a 20 bit resolution, means its quantization noise power should be 122 decibels lower than the signal power. But we are only seeing it's 92 decibels lower, which means it's not quantization noise that is dominating, it is some other source of noise. So we will normally call it thermal limited or jitter limited ADCs. Depends on which source is dominating. We will call that as limited by that. So it can be a thermal noise limited ADC, it can be a clock jitter limited ADC, the sampling clock used in the ADC. If that has a jitter, that can also unnecessarily corrupt your signal, corrupt the sampling process and therefore the signal itself. So what is important is whenever you are having a high resolution ADC, these ADCs also will by default have very low thermal noise. So we can model the ADC's noise at the input. Okay, as a independent noise source, we can model it as an input referred noise of the ADC. Now when you are amplifying the signal and feeding it to an ADC using a different input instrumentation amplifier, the noise added by this guy, the instrumentation amplifier noise, should be much smaller than the noise added by the ADC itself. For high resolution ADCs which have high ENOB, effective number of bits can be very high. In such cases, you need to have very low noise amplifiers. The amplifiers will definitely add noise. That should be much lower than the permissible noise due to effective number of bits. So for example, if the effective number of bits is 15, which means your SNR is approximately 92 decibels. Okay, so I can then back calculate what should be my noise power. So if for example, if your SNR is 92 decibels, I can no longer call it SQNR because it's now dominated by some other source of noise. So I'll simply call it a signal to noise ratio is 92 decibels. Assume your signal power, if you assume a 1 volt signal, 1 volt peak, then the signal power is given by V peak square by 2. So it will be 1 square by 2 or 0.5 volt square. Okay. If you assume it to be dissipating on a 1 ohm resistor, we call it 0.5 watts. But we are talking in terms of voltages here. So 0.5 volt square will be the power of your input sinusoid. The power of your noise should be, 92 looks like a little bit, difficult number. So let me take it as, let me take it as 92 itself, or let me take it as 90 for ease of calculations. So the noise power, if I say it has to be lower, 90 dB lower, if it has to be 90 dB lower, then it means that it should be 0.5 divided by 10 power 9. This would be your Vn square, or the power of the noise should be 0.5 by 10 power 9 volt square, or 5 into 10 power minus 10 volt square. This should be your noise power. Okay, so let's assume, if you recall from our previous discussion, we looked at the data sheet of a instrumentation amplifier. We saw that the instrumentation amplifier's input referred noise was 1 nanovolt per root hertz. Okay, it was 1 nanovolt per root hertz. Now, if I compute it, this is the power spectral density. Assume it is thermal noise mostly. And we'll also assume that the sampling frequency of the ADC is say 100 kilohertz. The ADC sampling frequency is 100 kilohertz. So usually there will be when you're feeding this amplifier's output, you will pass it through an anti-alias filter. We can treat it like a brick wall filter, with a passband of fs by 2. Fs is the sampling frequency till 50 hertz. So it will from 0 till 50 hertz, 50 kilohertz, your noise will be a white noise. This is the noise due to the op amp. Now remember, let me give you this. The instrumentation amplifier's gain happens to be 100. Since 1 nanovolt per root hertz is the input referred noise, I can write it as 10 power minus 18 volt square per hertz as the input referred noise spectral density. So when this goes through the amplification G, it's a differential amplifier, differential single-ended amplifier, the output voltage will be G square times 10 power minus 18. So it will be 10 power minus 14 volt square per hertz. That's the spectral density at the output. This will be spread from 0 till 50 kilohertz. So you will have to multiply. If I want to find noise power totally, because I'm after passing it through an anti-alias filter with a cutoff frequency of 0 to fs by 2, which will be 50 kilohertz. So the noise will be spreading till 50 kilohertz. And this will be 10 power minus 14 volt square per root hertz. So let me make another point. Let's assume this to be the one-sided noise spectral density. One-sided noise spectral density means we just take the negative noise and overlap it on the positive frequency noise. Okay, so one-sided noise means it will be usually 3 decibels more than the two-sided noise spectrum. So this is 10 power minus 14 volt square per root hertz. Now the area under this curve will give me the overall noise power. So that will be 10 power minus 14 times 50 kilohertz, which can be written as 10 power 5 by 2. So this is 10 power minus 9 by 2. So it is 10 power minus 9 by 2, or 5 into 10 power minus 10. Okay, so in this case, if you see, right, the thermal noise added by your instrumentation amplifier is as high as the input referred noise of your ADC itself. The input referred noise power of the high resolution ADC itself, which still may be okay. It will lead to some, maybe a 1 bit degradation, half a bit degradation. What do I mean by half a bit degradation is that, see, initially you had an SNR of say 90 dB. I'm just taking for ease of computation, say 90 decibels was your SNR. Now the noise power is doubled because I'm adding the same noise. Okay, the noise power that I am adding due to the instrumentation amplifier is same as the ADC's input referred noise, 5 into 10 power minus 10. Okay, so because it is same, the noise power will double. Signal power will remain the same. So S by 2n means if noise power is doubled, then the signal to noise ratio will go down by 3 decibels. It will become 87 decibels. On a dB unit, if you take 10 log of signal power by noise power, 10 log of 1 by 2 is minus 3 decibels. So 19 minus 3 is 87 decibels. So if you guys recall, 6n plus 1.76, if I degrade this by 3 decibels, that is equivalent to n. If let's say n reduces by half a bit, n minus half, so then your SNR will become 6n plus 1.76 minus 3. So for you to degrade your SNR by 3 decibel, it amounts to degrading your number of bits by half a bit. So which is why I said you will lose half a bit in resolution. So this is the kind of calculations you'll have to do. Okay. So you might, if let's say you picked up a poor quality instrumentation amplifier, let's say its noise instead of 1 nanovolt, it turns out to be 100 nanovolt per root hertz. If it is 100 nanovolts per root hertz, then you'll have to multiply this number by the overall noise power will become 10 power 4. I have to multiply. This will be 10 power minus 10 volt square per hertz. And this has to be overall noise power gets multiplied by 10 power 4. You can see, right? The noise power will be much higher, 10 power 4 times higher than the ADC's noise itself. So this guy's noise, the instrumentation amplifier's noise, can completely saturate, can completely degrade the performance of your ADC. Okay, so that is why when you're interfacing it, an instrumentation amplifier to a high resolution ADC, high resolution means very low input referred noise ADC, then naturally the noise due to the instrumentation amplifier also has to be very low. So that's how you pick it up. I gave one example to show you guys how does one do the calculations. I took an example of a ADC with, say, I think I took an example of a 90 degree SNR. Even though it's a 20 bit ADC, I said it's a 90 dB SNR, which from that we calculated assuming a signal peak of 1 volt. Plus minus 1 volt is the peak to peak input at the ADC's input. We calculated what should be the noise power. We should ensure that the noise power contributed due to the instrumentation amplifier has to be much lower than this number. If it is higher than this number, higher than the noise of the ADC, then you will degrade the SNR of the ADC further, right? You are adding a new source of noise. So your ADC's SNR will go down even more. Okay, which would then give rise to erroneous results. So that's how, if you want to pick a instrumentation amplifier that is driving a very high resolution ADC, then naturally the instrumentation amplifier's input referred noise has to be very low. Okay, so and how low, that depends upon your system. I showed an example of a 90 dB SNR ADC and what should be the rough range of required input referred noise for that. Okay, so that's what I've discussed, and this is a calculation that I'll do. Also guys, if you have some doubts, my intention of the YouTube videos is that I'll try my best to present you information that you may not find anywhere on the internet. That's what my intention is. So in case if you have any doubts, specific doubts, write me in a comment. If not, in the next video, I'll someday, definitely get back to your question. Okay. Yeah. Thank you.